Previously, we had introduced the idea of energy being sort of a natural money that nature recognizes, that it stays conserved in certain interactions. We're going to make that more concrete here by coming up with the work kinetic energy theorem. But before we can do that, we need to take a bit of a detour and introduce a new vector operation called the dot product. So previously we had seen that you could take a vector and multiply it by a scalar, and that would change its length, and if it was negated, also its direction. This is a different kind of operation. This one involves two vectors, and what they do is they show how parallel two vectors are. So I'm just going to draw two arbitrary vectors here. Let's call this one A. And this vector here we will call B, like so. And let's go ahead and say that the angle between them is phi. The dot product of A and B, where you write A, then you have a raised dot, B, and this is read as A dot B. A dot B is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them, in this case phi. Now, if we take a look at this, we can see that we could swap the order of A and B and get the same result. So the dot product commutes, so A dot B is equal to B dot A. When we get to cross products, which is a different vector operation that we'll introduce later, we'll see that that is not true for cross products, but for dot products it is true. And what we can see that we get out of this is we put two vectors into this operation. What we get out is a scalar quantity. Now, if I go ahead and project the drop a perpendicular down from A onto B, this piece here is the part of A that is parallel to B. So we can call that A parallel. And we can get that piece of it by saying that that is equal to A, and since this is the adjacent here, that would be A cosine phi. So I could grab my A and my cosine phi together, and I could say that A dot B is equal to A parallel times B. Now, by the same token, I could have instead chosen to project B along A like so. So here I'm dropping a perpendicular of B onto the ray defined by A. And this piece right here, which is longer than A itself in this example, would be B parallel. And this would be, oops, here, let me redraw that. This piece here would be B parallel, and that would be equal to B cosine phi. And so I could have decided instead to lump the B cosine phi together and say that that was equal to A times B parallel. And all of these are equivalent expressions. So we get this is that the more parallel two vectors are, the bigger the positive number will return, or if they are anti-parallel, you'll return a negative because the cosine of an angle bigger than 90 is negative. So the more anti-parallel they are, the bigger the negative number you'll get. For perpendicular vectors, that will give you an angle of 90 degrees, and so that will give you a dot product of 0. So if two vectors are perpendicular, the dot product is 0. Now, a handy thing to remember for the unit vectors is I hat dot I hat. These are two vectors of length 1, both pointing in the plus x direction. So the angle between them would be 0. So this would be equal to 1. By the same token, j hat dot j hat and k hat dot k hat will also return 1. Any other combination of them is going to be perpendicular. So for instance, I dot j or I dot k, or j dot k, or you could flip these because the cross products, sorry, the dot product commutes. Those will all return 0. So I may as well just for completeness say j hat dot I hat equals k hat dot I hat equals k hat dot j hat equals 0. So those are all 9 possible permutations of dotting the unit vectors together. So this gives us another way that we can find the dot product of 2 vectors. If we have a component representation of them, so if we break this apart, A dotted with B would be AX I hat plus AY J hat plus AZ K hat dotted with same thing but B's. There we go. So if we followed this through, most of the cross products are going to give us 0, but let's just follow it through to be explicit just once. So what we'll have here from the first 2 terms, you're going to have AX times BX, and then you'll have I dot I. And I just pulled out the AX and the BX because they're scalars. So I go ahead and brought them to the front and then left the I dot I to fend for itself here. And I'll go and pick up the next term. So AXBY I dot J plus AXBZ I dot K. Oops, not plus, dot. I dot K hat. All right. Then we can continue this sleigh ride here. So this will be plus. Now we'll do AY BX. So this will be J dot I plus AY BY J dot J plus AY BZ J dot K. Then finally doing this for the Z component, AZBX K dot I plus AZBY K hat dot J hat plus finally AZBZ K hat dot K hat. All right, that's a mouthful, but let's see what we get out of this. Well, I dot J, that's 0. I dot K, that's 0. J dot I is 0. J dot K is 0. K dot I is 0. K dot J is 0. And for the remaining ones here, I hat dot I hat is 1. J hat dot J hat is 1. And K hat dot K hat is 1. So what we're left with is that A dot B can also, A dotted with B can also be written as AX BX plus AY BY plus AZ BZ. So multiply the X components together, multiply the Y components together, multiply the Z components together, add them all up. So let's go ahead and work a quick example of that here. Let's say you have the vectors. Let's make this vector here A is 2, 0, 0, and then we'll say that B, that looks pretty good, is equal to 2, 2, 0. Of quick moment's reflection here, you should be able to convince yourself that this angle is 45 degrees. That's just because this would be 2, that would be 2. So you have a 45-45 right triangle. So let's just go ahead and find this 2 different ways and see what we get. Well, one way we could do it is we could observe that the magnitude of A is equal to 2. And the magnitude of B is equal to the square root of 2 squared plus 2 squared, which is going to be 2 square root of 2. Okay, so we can say that A dot B is equal to AB cosine phi. Well, this will be equal to 2 times 2 root 2 times the cosine of 45 degrees, which is 1 over the square root of 2. So get 2 times 2 is 4. Or, since we've got the vector components, we could also do this by saying it's equal to ax bx plus ay by plus az bz. So this will be 2 times 2 plus 2 times 0 plus 0 times 0 is 4. So either way works. Whatever is most convenient for you is the right way to go ahead and do the problem. Alrighty, in the next video we'll go ahead and actually introduce work and set up the work energy theorem. So we'll catch you over there.